The biggest surprise in microrobotics is not what we can build. It is what we cannot reliably verify inside the body. At micrometer to millimeter scales, control is only half the problem. The other half is proving where your device is, what it did, and what it left behind. Start with the physical reality of the small. In this regime, surface forces dominate. Fluid drag dominates too. Brownian motion is no longer a footnote. It is a design constraint. Diffusion, heat dissipation, and limited electromagnetic field penetration all press in at once. Even if a mechanism works on a bench, the body is opaque, deformable, and constantly moving fluid. So the frontier is not tiny gears or tiny swimmers. The frontier is reliable, controllable physical intervention, under conditions you can measure and defend. That is why, as of 2026, clinically credible microscale intervention concentrates in a few grounded areas. Targeted drug delivery is one, nanoparticle and carrier engineering is another, image-guided minimally invasive tools are a third, and microfabricated components, the parts that make larger systems more precise, are a fourth. Fully autonomous in-body microrobot surgery, the popular mental image, is not the center of clinical reality yet. One of the most concrete proof points is also one of the most constrained. In 2017, micromotor-enabled active drug delivery was demonstrated in vivo for stomach infection treatment. That matters because it shows active delivery can work inside a living organism. But the setting matters even more. The stomach is chemically distinctive, physically confining, and relatively accessible. Those features make propulsion and fate assumptions more favorable than in blood vessels or deep tissue. So the right takeaway is not, microrobots are here. The right takeaway is, bounded compartments can support bounded microscale capabilities. Now pivot to the area that attracts the most funding and the most wishful thinking. Tumor delivery by nanoparticles remains biologically constrained. The challenge is not merely engineering a clever carrier. Tumors have heterogeneous vascularization. They have variable clearance dynamics. Immune interaction is complex. Interstitial pressure can block penetration. Off-target deposition is common. Across studies, low delivery efficiency and heterogeneous accumulation keep showing up as central constraints. These are not marginal issues to optimize away. They are core limits that shape what is clinically reproducible. That has a strategic implication. If you hear a claim that a new particle solves tumor targeting in general, ask for distribution data, not just mechanism stories. Ask how they quantify off-target deposition. Ask how they handle clearance and immune response. Then ask whether the same results hold across tumor types, stages, and patient variability. Without that discipline, you do not have a platform, you have an anecdote. Magnetic nanoparticles sit in an interesting middle ground, and they deserve attention. They are an enabling substrate for steering, imaging, heating, and manipulation concepts. External fields give you a way to influence microscale agents without onboard power. That is a big deal, because power delivery at small scales is punishing, yet magnetics bring their own translation gates. Safety is not automatic. Reproducibility is not automatic. Characterization is not optional. You need to know what you made, batch by batch. You need to know how it behaves in tissue. You need to know what happens if material is retained, or degrades, or interacts with immune systems over time. This is where measurement culture becomes a hidden determinant of progress. In biology, endpoints can be slippery, assays can drift, reporting can be incomplete. A major milestone here is the MIQE guidelines from 2009, which established minimum reporting information for quantitative real-time PCR experiments. That seems far away from microrobots, but it is not. Microscale medical systems live or die on biological validation. If your measurements are not reproducible, your safety and efficacy story is not real. A future equivalent of MIQE, tailored for microrobotic and microscale interventions, may be as important as any propulsion breakthrough. Manufacturing is the next gate that quietly kills ambitious prototypes. High-resolution fabrication methods are improving. VAT photopolymerization, for example, supports increasingly complex microscale geometries. Biofabrication supports advanced three-dimensional in vitro models and regenerative medicine scaffolds. Together, these tool chains can accelerate design, iteration, and testing. But medical adoption depends on unglamorous requirements. materials qualification, sterilization compatibility, process validation, batch-level traceability. If you cannot tell a regulator exactly what is in each unit and how it was made, you do not have a product. You have lab art. There is also a systems point that senior leaders should keep in mind. The nearer-term wins will not require full autonomy. The more plausible path is to embed sub-millimeter mechanisms, sensors, or drug release modules into image-guided clinical workflows. Think of microscale capability as a layer inside catheters, endoscopes, and minimally invasive tools. Localization and verification can then lean on existing imaging and procedural discipline. That is why imaging and interventional infrastructure matter so much. You cannot control what you cannot localize, and you cannot scale what you cannot verify. So what are the hard research questions that separate science fiction from deployable categories? First, localization and tracking in opaque, flowing, deformable tissue without imposing unacceptable burden. That burden could be magnetic field strength, acoustic intensity, imaging dose, thermal load, or chemical effects. Second, clinically meaningful delivery thresholds. Not does some payload arrive, but how much arrives, how consistently, and at what off-target cost. Third, safe actuation beyond favorable compartments. Propulsion that works in the stomach may fail or become unsafe in vascular or deep tissue settings. Fourth, material fate over clinically relevant time horizons. Degradation products, retained particles, polymer residues, and payload leakage all need characterization. Fifth, test systems that predict in vivo behavior before animal or human studies. Biofabricated models help here, but they must correlate with real transport and immune interactions. And sixth, medical-grade repeatability and microfabrication, where multi-material interfaces and tiny tolerances amplify variance. Design automation also enters the story, but with a warning label. Optimization methods, including genetic algorithms, can search morphology and control policies. They can also overfit to simplified simulations. At microscale, simplified models are especially dangerous. If your simulator does not capture tissue variability, flow regimes, adhesion, or immune interactions, you may be optimizing for a world that does not exist. Over long horizons, progress likely compounds in layers. Near term, from 2026 to 2050, expect targeted carriers, magnetic and material platforms, image-guided microsurgery, microfabricated components, and tightly bounded active delivery demonstrations. Mid-century, from 2050 to 2100, semi-autonomous systems may become plausible in constrained anatomical compartments, but only if localization, safety, manufacturing repeatability, and evidence standards converge. Beyond that, microscale engineering could become a routine layer of regenerative medicine and closed-loop sensing, but only where biological response and material fate are governed. General-purpose autonomous in-body surgeon swarms remain speculative, mainly because verification and control do not get easier as systems shrink. For capital allocation leaders, the practical move is counterintuitive. Fund the enabling layers before funding autonomy narratives. Invest in biodistribution analytics and benchmarking. Invest in magnetic material characterization. Invest in microfabrication quality assurance and traceability. Invest in biofabricated test models that actually predict in vivo behavior. Invest in standardized endpoint measurement and reporting discipline. These are not support functions. They are the roadbed that makes the rest real. Also build mixed teams on purpose. Microfabrication alone will miss pharmacokinetics. Materials science alone will miss imaging physics. Robotics control alone will miss clinical workflow and trial design. Regulatory evidence generation cannot be bolted on at the end, especially for combination products where device and drug risks intertwine. Finally, treat governance as part of the technical spec. Untracked particles, covert payload delivery, uncontrolled degradation products, and irreproducible measurements are not only scientific risks, they are liability and trust risks. They demand audit trails, pre-market evidence, and post-market surveillance. If you remember one line, remember this. At Microscale, the winners will be the teams who can measure, localize, and prove safety, not just the teams who can move tiny machines.